Today we will see in detail the Ehrenfest theorem, which connect classical physics and quantum physics. So you know very well in quantum mechanics we are dealing all with the operator. In classical mechanics, these things are the observable. For example, X is operator in quantum mechanics, whereas it is observable in the classical mechanics. So from the Schrodinger fixture, we know the time derivative of expectation value of X is equal to 1 over I h cross expectation value of X with Hamiltonian H. If it does not depend explicitly on time, there is we will get one additional term which we are ignoring because it does not depends explicitly on time, so this will be 0. Then the Hamiltonian is equal to p squared over 2m plus v of x. You know the x will commute with potential, that is potential depends only on x. So only non-commuting term is p squared over 2m. So this can be rewritten as 1 over I h cross commutation expectation value of commutation of x with p squared over 2m. Since 1 over 2m is constant, we are taking that out. That is 1 over, already there is I h cross 2m. This x p squared I am writing as p into p. So using commutator expansion, we can rewrite this as the expectation of x with p, and this right hand side p I am taking to right hand side, and the left hand side p I am taking to the left hand side. So we got this. We will simplify this. So now we got this expression, commutation of x with p is I h cross. Here also I h cross. So I h cross is a number, you can bring this back and forth. So this will be this can be written as I h cross p. Here also I h cross p, which will become if you add these two, you will get 2 I h cross p. So here this I h cross 2 you can cancel with this 2 I h cross. So only p in the numerator. Numerator you have the expectation value of p. In the denominator you have 1 over m. So the time derivative of expectation value of x is equal to 1 over m, the expectation value of x. You can see the classical counterpart, that is dx by dt, which is velocity, is equal to p is mass into velocity divided by mass. You will get velocity. So this can be written as dx by dt is equal to 1 over m into p. So this is a classical analogy. So this connects the quantum physics and classical physics. Only thing is here we are dealing with the operator. In classical mechanics we are dealing with the observable. This is in one dimension. Same thing in three dimension can be written as the time derivative of r, expectation value of r, because it's in one dimension. In three dimension x is replaced as r, which is equal to 1 over m expectation value of p. So far we have seen Ehrenfest first theorem, that is time derivative of expectation value of x. Similarly, we can find the time derivative of expectation value of p. By definition is equal to 1 over I h cross expectation value of commutation of p with the Hamiltonian if there is no explicit time dependence. So now the Hamiltonian is p squared over 2m plus v of x. So here p squared will get will commute to each other. So this can be ignored. Only thing is v of x. So we can write the time derivative of expectation value of p. We are making a arbitrary function pi. So this can be rewritten as 1 over I h cross minus p operator p is minus I h cross delta over delta x v of x pi, which act on the arbitrary function pi. So this can be written as, here you can see IH cross and this IH cross will get cancelled. So you will get only negative sign you take outside. Then it will become the expectation value of delta over delta x with v of x, and you have pi outside. So this can be written as commutation of a with p is equal to ab minus pa. Here this partial derivative is A, this potential is P. So AB is equal to uh, delta over delta x V of x, and you take care of this pi also, V pi, and minus PA. P is V of x, and this A is equal to delta over delta x, and you take care of this pi. So I have taken this. Then we will try to reduce this. Now we got this relation. First you expand this first term of the right hand side. This is a UV differentiation. So first you keep V as it is and differentiate pi. So this will become V delta pi over delta x. Then you keep pi as it is and differentiate the V. So this will become pi delta over delta x V, and you have third term as it is v delta pi over delta x. So you compare this first and third term, both are equal and negative, opposite sign. So this will get cancelled. And also you can remove this pi both sides. So then you will get the expectation value of time derivative of expectation value of momentum is equal to minus delta v over delta x in one dimension. That is, what is a time derivative of momentum? It is nothing but force, rate of change of momentum is nothing but force, which is equal to negative gradient. So in one dimension it is equal to this. Uh, that is delta over delta t, that is, sorry, time derivative of the expectation value of momentum is equal to the negative gradient of potential. So this is in one dimension, this is in three dimension. Then we will move further. So we got two relations, that is a time derivative of r, expectation value of r in three dimension, which is equal to 1 over m, the expectation value of p, and the time derivative of a expectation value of p is equal to a negative gradient of the potential. This Ehrenfest theorem are analogous to a classical equation of motion, that is Tr over Tt is equal to P over m. So I have explained that this is velocity, this is mass, momentum is mv, mass into velocity. So mass will get cancelled. It is exactly equal to the velocity. Second one is we know here, see the analogy, we are replacing operator into observables. Here the expect, so we are removing the expectation value. So here also same thing. Here negative gradient of potential is force. Force is equal to Tp by Tt. Uh, that is Tp, which is equal to mass into velocity. M is mass into velocity. This can be taken as dv by dt. So naturally F equal to ma. Newton's law of motion. So there is a link between classical physics and quantum physics. So Ehrenfest theorem provide an example of the correspondence principle since it shows that wave packet moves like a classical particle. So this is analogous to classical particle movement. Whenever the expectation value gives a good representation of classical variable. So this is our conclusion. Thank you very much for watching my video and supporting me continuously. Thank you very much.